polynomials with a degree of 1, like a line, and you know how to graph polynomials with a degree of 2. Oops. So a degree of 1 is a line. We use a totally different technique on a line. Obviously, we use y equals mx plus b, the slope, the intercept, and the slope. When there's a degree of 2, which is a quadratic, we also use unique techniques to a quadratic, like finding the vertex and finding the 2x intercepts, or maybe no x intercepts, or maybe 1x intercept. But we find the vertex and we find intercepts to graph quadratics. Everything beyond this, degrees of 3 and higher, we're going to use this technique. Before we jump into any of these, I want to talk about end behavior rules. So you essentially have to memorize what I'm about to write in here. But I will tell you that if you base your knowledge off what you know about lines and quadratics, I would argue that you actually already know these rules. Okay? So starting with an odd degree, which we'll use lines as our sample. But an odd degree polynomial is when your highest exponent is a 1 or a 3 or a 5 or a 7. Well, lines fall into having a degree of 1, so they would be in this category. So if you have a positive leading coefficient on a line, for example, think about y equals mx plus b. If m is positive, what do you know about the end behavior? Does it start low, end high? Like this, starting low, ending high? Or does it start high, end low? If your m is positive, does it start low, end high, or start high, end low? What do you think, Jason? Right, because a positive m means a positive slope, so it starts low, ends high. Now, with other positive odd degreed, it'll be a little bit more interesting from start to finish, but it will still start low and high. It will have more fluctuations along the way than a line does, because a line has none. But it will still start low and high if it's a positive 2x cubed, for example, or a positive 3x to the 7th. And vice versa, if there's a negative leading coefficient, like a negative slope, we know it starts high, ends low. And again, when it's to the third power, it'll be a little bit more interesting in between, but the general overall slope, start to finish, will be negative still if it has a negative coefficient. And if it has a positive coefficient, the general overall slope will be positive. Do you follow? Okay. Now, as far as the quadratics, which you already know about, and whether you're going to the second power, to the fourth power, to the sixth power, an even degree polynomial will follow these rules. Your leading coefficient in a quadratic is your a value that we talk about. And what do you know about what does a quadratic do if it's a positive a? How does it open? Opens up. So that would be starts high, ends high. Opens up. Now again, with quadratics, a positive quadratic just flat out opens up. A positive 4th degree polynomial, a positive 6th degree polynomial will be a little bit more interesting in between, but it will still open up if it's a positive even. And if it's a negative a value out in front, we all know that that opens down, starts low, ends low. But again, a parabola is very straightforward and simple. A negative coefficient on a fourth power or a sixth power will be a little more interesting, but it will still open down. Okay? So as far as quadratics, we talk about opening up, opening down already. So we can continue that with even degrees. And in linears or odd degrees, we talk about slope. This is technically a positive slope overall. And this is a negative slope overall. The one thing that should become obvious, when you look at odd degree and behavior, it does different things on either end. If one end goes towards positive infinity, the other end goes towards negative infinity. It has opposite end behavior. Opposite. Whereas even degree polynomials have the same end behavior. Either they're both going towards positive infinity on both ends, or they're both going towards negative infinity. Now, when I put this little chart together, I use very informal math language, like starts low, ends high. Like if I were to kind of describe this behavior more formally, rather than saying starts low, ends high, the proper notation would be like this. As x approaches negative infinity, so that means we're going left, what is y doing? Where's the y coordinate headed if I'm going this direction? Negative infinity. And as x approaches positive infinity, what's my y doing? Positive infinity. It's just that's a lot less common language. So I find it easier to say it starts low, ends high. But truthfully, you'll see it this way. If I go over to this one, let's just do an even example. As x goes towards negative infinity. So that would be me heading to the left. So going this direction. What's happening to my y coordinate? It's going down towards negative infinity. And as my x on this one goes towards positive infinity, which means I'm headed to the right, where's my y coordinate going? Also going towards negative infinity. So you'll see what I mean by same end behavior. Doesn't matter on an even one if your x is going towards negative infinity or positive infinity. They're both going in the same direction on both ends. Versus odd ones will be opposite of each other. So that just kind of illustrates 2 of the 4 written properly in math language. Okie doke. Any questions? All right, so if we go back up to the top and we have to graph polynomial functions, you want them factored. So if you look at something like this, Eric, you do not want to start by multiplying them out. You want them in factored form because you're going to capitalize on the x-intercepts, which is when y equals 0. And if it's already factored, believe me, you'll get to a ton of them that are not already factored, and that's the first thing that you have to do is factor them. But if they're already factored, please, dear Lord, do not distribute that out and reverse all that work and make yourself have to redo it. So it's already factored, so we can set the y equal to 0 and essentially tee it up. And where are our x-intercepts? If we tee this up, what x values will make this true? Lucas? 3, because if we tee this up, we get x equals 3. So I'm going to guesstimate that that would be right around here. And when we tee up this one, if x plus 1 equals 0, we get x equals negative 1. Now, there is a difference between this factor that gave us 3 and this factor that gave us negative 1. What do you notice that's different about this factor versus that factor, Haley? Right, the second one is squared, which does affect your graph. This is where the concept of multiplicity comes in. Write that word. If your factor is just being raised to the first power, like the x minus 3 is technically, it has a multiplicity of 1. And that's going to create something different than what happens on the x plus 1 factor, because that has a multiplicity of 2. When they have a multiplicity of 2, I want you to think of the key word bounce. Which means when my graph touches that root, it's going to bounce off of it and come back in the other direction. Versus if something only has a multiplicity of 1, it just is a straight cut. We'll call it. It just is going to go straight through it. You've seen this already with parabolas without really realizing it. If you have two separate roots, this cuts straight through, and this one cuts straight through. But if you have the same root twice, it bounces. That's multiplicity of 2. These are each multiplicity of 1 and 1, right? Okay? With a quadratic, it should add up to 2 roots in total. 2 roots should be accounted for. Here we have 1, 2, and here, because this is a bounce, we consider that as being the same root twice. This one has how many roots? 1 from this one, because it has a multiplicity of 1, and 2 from this one, with a multiplicity of 2. So what is the degree of this overall? If we have a degree of 1 and a degree of 2, what's our total degree? 3. So when we go to follow our rules here, we're following our rules for odd because it's a degree of 3. Is this leading coefficient positive or negative? Positive. So overall, we want a positive slope, which means we're going to start low and end high. Now, which one was the double root? The negative 1? This was a double. So when I get to this root, I have to bounce off of it. And then I don't really care where you turn around, but you have to turn around at some point and go through. This was a single root. So we just cut straight through. And that whole overall positive slope of starting low, ending high, should take care of itself if you've bounced or straight cut through properly. Okie doke. The only other thing you'll be asked to label is the value of the y-intercept, because you can easily find a y-intercept by setting x equal to 0. So if you do that and you set x equal to 0, it'll be 2 times negative 3 times 0 plus 1 is 1 squared. What does all that give you? What's 2 times negative 3 times 1 squared? Negative 6. So the only thing you may be asked to do is label your y-intercept. Your roots and your y-intercept. Any questions? Okay. Let's jump to the second one. If we tee this up, negative 2x plus 5 equals 0. Subtract 5 from both sides. divided by -2. What is the degree of that root? 2.5. What was the degree of that factor? What's the multiplicity of that factor? All the same question. 3. -2x plus 5 was raised to the third power. So this is the last one I'll tell you about. A multiplicity of 3 we're going to refer to as a squiggle. You'll see why I say that once you see it in action. And then x minus 4 has a degree of what? 1. Those aren't really scaled well, but I didn't want them on top of each other. Okay. What is the overall? So before we start drawing, we have to decide, is this starting high or is it starting low? What is the overall degree of our function? 4, exactly. 3 on this root, 1 on this makes 4 total. Now, this is a little bit trickier as far as the leading coefficient. We don't have to multiply everything out. But when you cube -2, what will it be? What's -2 times -2 times -2? -8. And the leading coefficient here is 1. So our leading coefficient will equal -8. So this is an even degree polynomial with a negative leading coefficient. So it's going to open down, which means it starts low, ends low. So I'm starting low. I'm going to approach the 2.5, and I'm going to show you before you do it what a squiggle looks like. When you approach 2.5, if you're doing like a squiggly line, it looks like it's going to turn around and be the top of a parabola, right? But what actually ends up happening on a squiggle is it kind of inverts. And on the other side, looks like it'll be like the bottom of a parabola. Does that make sense? You don't have to be perfect about your squiggles, but I want to kind of see that. And then I don't have much time, but I have to turn this around fairly quickly and come back down through the 4. And 4 was a single root. So again, what naturally should happen is I should have this opening downward as it was supposed to. As long as you start right, it should end right if you're bouncing, wiggling, or cutting through appropriately. Okay? Hold on, last one. Where's this root? Hello? Hello, kids. 1/2. And it's a double root, so that's going to bounce. And where's this root? -3. And that's a double, so it's going to bounce off of that as well. Overall, what's the degree? 4. So it's either opening up or opening down. The leading coefficient will be a -2 squared, which is 4, times a 1 squared, which is a 1. So the leading coefficient is a 4. So positive. So is it opening up or opening down? Up. So it's going to bounce off of -3. It's going to bounce off of a 1/2. And we're all done. Make sure it doesn't cross the x-axis in an additional location that it's not supposed to. Right? It can only cross where your roots are.